Hello everyone, so welcome back again. So in this segment, we're going to see the BFS algorithm in a graph. So when we talk about the BFS algorithm in a tree, we know that we are going to always start the BFS algorithm from the root node, okay? But a graph means, it's a collection of node and edges, okay? Now, when we run a BFS algorithm in a regular graph, we are going to need one more input. Okay, so we need the graph itself, and we have to specify the node where we're going to start the BFS algorithm. Okay, so it can be any node from the graph, but in the specific BFS algorithm, we have to specify from which node we are going to run the BFS algorithm. All right, so here you can see that in the BFS algorithm, we need two input, the graph and the node S. Okay, S is a node known as a single source node. Okay, means only one node. This node is going to work as a source node, means from this node we are going to systematically explore all the node from starting this node. All right, so the main idea of BFS algorithm is same. Here also we start from the source node, and first we are going to find the immediate neighbor of the source node. Then systematically starting from all the immediate neighbor, we're going to explore all the neighbors in the next level. All right. So here what we need, initially we're going to initialize a distance variable. Okay. So distance variable, and this distance variable will keep track of how far from the starting node and whether we have seen the node yet. Okay. All right. So from the BFS algorithm is also starting from the source node. It will give us the idea how far each of the node is from the starting node. Okay. For example, node C has actually the distance 2 from node A. For example, we have to reach node C from A, like first we have to traverse B, then C. Okay, but node G is 3 steps away. For example, I have to go to B, then F, then G. Okay, so we'll see that, but BFS algorithm will also give us the idea, and we'll have a initial distance variable. Okay, and this will keep track of how far from the starting node and whether the node is already visited or not. So in the graph, how this is also different from a tree, in the graph we can have a cycle. Okay, so starting from node A, we can visit B, E, and D. But when we are at node E, from node E, we can also visit A again. Okay, so we do not want to visit a node more than once. Okay, so every node has to be visited only once. All right, means we cannot actually we cannot make ourselves stuck in a cycle. Okay, so every node is going to be visited only once. All right, so that's why there is an additional variable dist. All right, so what actually we are going to do, let's look at the algorithm line by line, and we'll see how we are going to make the traversal in a graph. All right, so initially for each variable, it means for each node in the vertex list, we're going to make the dist variable for each vertex infinite. Okay, initially we're going to do that. So initially it will be infinite. Okay, so this infinite means, so when the dist of a node is infinite, that means two things. Okay, it means that the distance from source is unknown. Okay, and also means that the node is not visited yet. Okay. So let's see here, we have 1, 2, 3, 4, 5, 6, 7 node. Okay. So if we have a distance variable, sorry, distance array, all right, and if the distance value of a particular node, okay, so this is, let's say this is the first node A, okay, this is the first node A, and the distance variable for the node is infinite. That means that the distance from the source is unknown. We do not know what is the distance from the source, and it also means that the node has not visited yet. Okay, so first we are going to set all the nodes unseen, mean unvisited. Okay, then we are going to check whether node has been visited or not. Okay, if not visited, then only we are going to explore the node, and we are going to update the value of dist variable. Okay, so let's do that, and let's see how this is work. So first, actually, we're going to make the source node, the dist variable of the source node 0. Okay, so we're going to make the dist variable of source node 0. So what does that mean? That means actually the dist from source to A is 0. Okay, means the distance from the source node, this A is itself the source node, so distance from source to A is 0. Okay, here also we're going to use the data structure queue. Okay, and we are going to enqueue the source node in the queue. All right, and we'll run a loop until the queue has some value. All right, and queue is not empty. So we're going to dequeue the item from the queue. We're going to make it visited. Okay, and we're going to explore all the immediate neighbor of the node. Okay, say for example here, right now we have only the node A in the queue. Okay, so we're going to dequeue the node A. Okay, we have dequeued the node A. All right, so queue looks like empty, but what actually we're going to do, we're going to make node A visited. Okay, let's update the visited array like this. We'll make A visited. Okay, so what now we're going to do, we're going to explore the edge of A, and we're going to explore all the immediate neighbor of A. Okay, so immediate neighbor of A we can explore by following the edge B, E, and D. Okay, so what we are going to do with them, first we are going to enqueue them. Okay, before that we are going to check that whether the dist value of this neighbor are infinite or not. So for example, here we have this node A, we found immediate neighbor B, D, and E. So if the dist value of these neighbors are infinite, that means they are not visited yet. Only if they are not visited yet, we are going to explore them. Okay, so that will make sure that we are not going to visit one node more than once. All right, so we're going to enqueue all of them. Okay, so now queue will look like D, B, and U. Sorry, D, E, and B. Okay, we're enqueuing all the immediate neighbors in the queue. All right, and we had in the visited list A only. All right, and this line, look at this line. What actually we're going to do, we're going to update the dist value for each node. And how we're going to update the dist value of each node, we are going to add 1 with the source node, means with the parent node. So we found this neighbor following the node A. Okay, so this is the immediate parent of this node B. All right, so what we are going to do, we are going to add 1 with the dist value of this node A. Okay, so A had dist value 0, so B will have 1, means 0 plus 1, 0 plus 1, 0 plus 1. All right, so B has dist value 1, E has 1, D has 1. Now, what does this dist value say? That if the dist value is not infinite means these nodes are actually has been explored, okay, explored by some node, and this value says that how far this is from the source node. You can see that B is actually one node away from the source node, okay. The distance from the source node to B node is 1, from E node from A to E is 1, from A to D is 1. All right. All right, so we're going to continue with this while loop and let's see how this is going to work. We find that Q is not empty. We're going to we're going to dequeue from Q. So we dequeue D and we're going to explore the children of D. But before we explore the children of D, we had to have few checking. All right, for example, from D, we see that D has neighbor A and E. Okay, so D has neighbor A and E. For every children of D, first we're going to check what is the distance value. If the distance value is not, if the distance value is infinite, then only we're going to run these 2 lines of code. Means we are going to explore the node. Okay, we are going to explore the node and we're going to enqueue them. But looks like both of the children A and E, they have the distance value which is not infinite. Okay, means they are already visited by some other node, means actually we're not going to do anything. Okay, then let's dequeue E. So for E, we found it has 3 children, B, A, and D. So for every children, we'll check the distance value. Distance value is not infinite, means they are already visited, nothing to do. Okay, so now dequeue B. Okay, and in the meantime, actually, we're going to, whenever we dequeue some item, we're going to make it visited. Okay, all right, so dequeue B, and B has how many children? B has A, E, C, and F. Now A and E already visited. We can see that from the distance value, but C and F, they have the distance value infinite. So if the distance value is infinite, we're going to run these 2 lines. So we're going to enqueue them. Okay, we're going to enqueue in the queue C and F. All right, and we're going to update the distance value for C and F like this, distance of U plus 1. And we explored C from B. Okay, so the distance value here will be 1 plus 1 equals to 2. All right, and F distance value will be also, we are exploring F from B. So it will be also 1 plus 1 equals to 2. All right, and we make B visited in our visited list. All right, so again, dequeue C. So C doesn't have any other unvisited children. C has only 1 children, B. Okay, but B is already visited, so nothing to do. Okay, so we make C only visited. All right, so then we dequeue F. F has 1 unvisited children, G. Okay, so we are going to enqueue G. We are going to update the dist value like 2 plus 1 because F has dist value 2. So it will have dist value 2 plus 1 equals to 3. Okay, and we are going to okay, so so in the next iteration we are going to dequeue G. G doesn't have any children, so nothing to do, and we're making G visited. All right, so before that we'll make F visited and then G. All right, so you can see that first we visited A, the level 0, then A has immediate neighbor B, E, and D. So we explored D, E, and B. All right, then starting from B, the next level we had actually C and F. So we visited C and F. Okay, and then G. All right, so the final, that's how in the graph BFS traversal also, we are visiting them level by level. Okay, so let's go back again one more time how it is going to look like. Okay, so you can see that first we visited A. Okay, then from A we visited D, E, and B. Okay, so then we visited C and F, then we visited G, and finally this will be our tree. The color blue means they all are visited and they are done. Okay, visited and done. Done means actually this will make sure that we'll not visit one node more than once. All right, and the value of the dist, okay, the dist value for each node, it has a very useful information. Here you can see that the node has value 0, means the distance from the source node is 0. Obviously this itself is the source node. Now from the source node, the distance from B, D, and E is 1. The C and F has distance from the source node is 2. You can see that this is the distance, and this is also the shortest path distance. Okay, you might want to visit F by following the path like A, D, E, B, and F. Okay, but this is not actually the shortest path. So this value is also going to give us the shortest path distance from the source node. Okay, so again G has the shortest path distance from A is 3. So AB, BF, and FG. All right. All right. So runtime of BFS algorithm. So in the BFS algorithm, actually, if we use the adjacency matrix means the size of the matrix will be size of vertex times size of vertex. Okay, so if we have in this example, if we have a graph with 7 nodes, okay, so means the adjacency matrix will have dimension 7 times 7. Okay, so if we use adjacency matrix, in that case the runtime of BFS algorithm is going to be order of V square. So here V is the size of node. Okay, so V is the size of node. All right, but if we use the adjacency list, okay, in that case the runtime of the BFS algorithm is going to be order of V plus 1. I'm sorry, the runtime is going to be order of V plus E. So here V means size of nodes and E means size of edges. Okay, so why that makes a difference? Because I mean, if we have a adjacency matrix, okay, so in adjacency matrix actually we have to traverse the whole row for each node. Okay, we have to traverse the each node, and we have to traverse the whole row for each node to see whether there exists an edge or not. All right, for example, here we have A, B, C, D, E, F, and G. All right, so we have to traverse the whole row here, the full size for node A, to see what are the edges adjacent with node A. Okay, we have to do the same for node B, C, D, E, F, and G. Okay, that makes it actually 7 square. Okay, means n square. N is the size of vertex. All right, but in the adjacency list we know actually A has how many node. Okay, A has how many node adjacent to A. So B has how many node adjacent to B. All right, so if node C doesn't have any list, the list will be empty. Okay, so we do not have to traverse the list of node for the node C because list is empty. Okay, we can see that whether whether node C has any edges or not. All right, but in this adjacency matrix we do not have any idea because we have to actually traverse the whole matrix to see whether a node has a particular edge or not. All right, So if we use the adjacency list, the runtime will be order of V plus order of E. Okay, means we are going to traverse actually all the node, but for each of the node, we can find how many edges is adjacent with that node. Okay. All right. So the breadth first search algorithm will produce a breadth first tree with root S. So if we follow only the path that we traverse to explore all the nodes, we can see actually it will produce a breadth first tree. You can see that considering the source node as a root, it will create a breadth first tree. Okay, so these edges are the edges that we use to traverse all the node. Okay, explore all the nodes. All right, and the dist value for each node will correspond to a shortest path from S to V in the graph. Okay, so again you can see that if you have an undirected graph, okay, if you have an undirected graph, you can actually find the shortest path for every node from a single source using the breadth first search traversal. So I'm giving you for an exercise here. Here actually what we are going to do, you can see that this is the same graph, but in this example, we are going to run a BFS algorithm. And we're going to run a BFS algorithms using B as the start node. Means in this BFS algorithm, the input is G and S, but the value of S is B. Okay, so we'll run the BFS algorithm starting from B. All right, so you have to show the BFS tree and the shortest path distance value for each other node from B. All right, so try that by yourself, and we'll talk about that in the next segment. Okay.